Okay, so I've already put the notes on Putra Blast. So I hope that you have downloaded the notes from last week and also from this week. Okay, so for today, I'm going to discuss about how we can use machine learning, okay, to do classification of remote sensing imagery, especially I'm just going to take as an example on how we process hyperspectral imagery, okay, and later on, Mr. Yuhao will be explaining about how we use QGIS and also some plugins in QGIS in order to perform image classification. Okay. So from last week or in the beginning of the course, I have already explained why we need to do classification. You still remember why we need to do classification? Okay, why we need to do classification of the imagery? Maybe Putri Nur Farah can tell me why we need to do classification. Siapa nama Putri kat sini? Who is Putri?
Me, Doctor.
Yeah, so Putri.
To know the detail about the the location.
Okay, so classification is basically a technique that we use in order to identify, okay, the labels or the classes of the pixels that we have in our image. Okay, so it is also a way of I call it doing identification, okay, of the land cover or land use that we have, okay, in our area of study. Okay, so that is classification. Okay, in fact, there are a lot of techniques, okay, that we can use for classification. Okay, there are a lot of techniques that we can use for classification. So as I have listed over here, you can see on the slide, there are many methods. Okay, there are many methods. In fact, it is more than what I have listed over here. Okay, so okay, these are some of the common methods that are being used in the industry or for research. Okay, for doing classification. Okay, for example, we have spectral angle mapper. Okay, which is not an AI technique. Okay, but we have also AI or machine learning techniques. For example, the support vector machine, okay, the decision tree, the random forest, the artificial neural network, and deep learning. These are among the most popular methods, okay, based on machine learning. There are also other ways of classifying our data. For example, there is a technique called object-based image analysis or OBIA, okay, which is in general, what I can tell you is that there are three ways in general, okay, on how we do classification. Okay, the first one is entirely based on the spectral information of the pixel. Okay, and the second method is entirely based on the segmentation or the what you call it, the objects or the spatial component. And the third one is a fusion between the spectral and the spatial components in the image. Okay. But for today, I'm just going to focus on the spectral base. Okay. methods, especially those based on support vector machine and random forest. These are the two most popular and also simple ways of doing machine learning spectral-based classification. Okay. Okay, so as I mentioned, we are going to discuss some of the classifiers with a specific focus on SVM and also random forest for hyperspectral analysis. Okay, so classification, as I have already mentioned, is basically transforming your data from signals to labels. Okay, so when you have your imagery, your imagery actually for every pixel, if you analyze it for every single pixel, if you plot the component of a pixel in the image, so the image that you see on the screen, okay, so you might have downloaded Landsat, Spot, or Sentinel, any sort of remote sensing data, or even any digital data for that matter. So if you look closely, if you zoom in and zoom in, you will see that the image is actually consists of pixels. Okay, so for every single pixel, if you plot the component of the pixel, you can see the spectral curve, right? So all these spectral curves, correspond to some information or relevant information on the ground. So a specific spectral curve could tell you what is the land cover, what is the land use that we have in the image. So the process of classification is actually we are transforming the signal information to classes. All right. So once you have processed and transformed the data from electrical signal to labels, then you will get what is known as a map or a plan or whatever you might call it. But they are basically in the simplest term, it is a map, right? So later on, this map we will use in a GIS environment, or you can also produce the hard copy as well version of the map. Okay, so it can assist you for other to solve other problems or to get some information to help you in your decision making. Okay, so that's classification. Okay, so if you want to talk about image analysis, okay, if you want to talk image analysis itself is a very big the slide is not moving, isn't it? I don't know why when I enlarge it, can you see the full screen of this particular slide?
No, Doctor.
Okay.
It's not full screen.
I don't know why. It's not Gmeet is not displaying the full screen. Okay, anyway, doesn't matter. Even if I'm sliding, it's not transforming. It's not changing. A minute. I don't know why. Okay, but you still can see, isn't it? So it should be okay. I cannot make it a full screen. I don't know, for some reasons it's not happening. Okay, so anyway, when we talk about image analysis is actually is a very big field by itself. Okay, so there are so many things that we can do for if we have imageries. Okay, we can do anomaly detection. We can do spectral unmixing and so on. But for our specific requirements for us, for class, we just concerned about the classifications, okay, that we want to do with our data. Okay, so if you want to do a classification, okay, there are certain things that you need to that you need to have, okay, before we proceed with the classification project. Okay, for example, we need to know what we want to map. Okay, what is your objective in doing the mapping? What you want to see? Okay, what information that you want to extract? Okay, and then you also need to have some ground truth information. Okay, so meaning that you need to have some information about the area that you want to map. Okay, especially when you are doing supervised classification. Okay, especially when you do supervised. Normally in remote sensing, we prefer to do supervised classification, meaning that we supervise the computer, or we teach the computer what to extract. Okay, so even though the machine learning process can be divided into supervised, unsupervised, and also reinforced learning, but most of the work that we do in remote sensing are supervised. Okay, and in order to perform the supervised classification, you need to have some ground truth information, okay, as our reference. And then once you have got some samples or the reference, you can use the samples or the reference in order to train the classification algorithms. Okay, so when you want to train, okay, when you want to train or when you want to create the models, okay, for mapping, you can use, for example, a spectral match based image classification. For example, the SAM method I have already mentioned, the spectral angle mapper, or the statistics-based image classification. Okay, for example, support vector machine and random forest. Okay, and most of the time, I would say that the majority of the work in remote sensing are based on the statistics-based image classification or the machine learning-based image classification. Okay, so this is what we're going to use. The spectral angle mapper is a technique that is not based on any AI or machine learning. We are not teaching the algorithm to work on certain samples and perform the modeling. But this method is basically is a physical-based method where it determines the similarity of the reference and also the pixel. Okay, and this method is normally being employed, okay, in order for us to overcome illumination problems in the image. Okay, but because we are not going to use that, I'm just going to skip that for a moment. Okay, we are more concerned about the machine learning based classification. Okay, because in this process, we can what we say, we can develop some models, okay, for training. Okay, by having some ground truth information, we can use that to train a model, okay, and also deploy the model, okay, for larger scale mapping projects. So this is the pipeline, okay, or the methodology that normally we adopt, okay, in order to perform machine learning classification. Okay, I think you have come across a similar flow that I have mentioned in the previous weeks. Okay, so when you have a specific problem, either business or scientific, then after that you will get your data, and then you perform some initial data analysis, and after that you do model training and selection. Okay, so when you want to do model training and selection, you need to have the training and also the testing data. Okay, and after that you will deploy your model, okay, for the entire let's say entire image, right? because when you do a remote sensing image classification, your training and testing will be based on only limited number of samples, okay? Because it's not going to make any sense if you have to do extensive ground truthing, because the purpose of machine learning development is you want to reduce the manual manpower needed for mapping. Okay, so you just need to have some samples that can be used to train the computer or the algorithm. Okay, so once you have come up with the model, then this model can be deployed, okay, in order to do the classification for the entire image. The entire image will cover a very huge area that will be quite impossible for you to perform manually by using common manpower. Okay, so that's the point. So in terms of the machine learning process, okay, we can divide machine learning or computer learning into three types of learning. Okay, the first one is called supervised, the second one is called unsupervised, and the third one is called reinforcement learning. Okay, but we are more interested with the supervised one because we can control what are the labels, okay, what are the classes that we want to detect. Okay. On the other hand, if you the unsupervised one, we don't supply any initial information to the computer. We just let the computer run and identify the patterns. But the problem with the unsupervised is that you cannot know beforehand what are the labels, okay, or the classes that we want to determine. Okay, and the reinforcement learning is normally used for robot training, or maybe let's say, for example, if you want to train a self-driving car, okay, normally we will do reinforcement kind of learning. Okay, so okay, so under the supervised learning, under the supervised learning, there are a lot of classification, okay, that you can choose. Okay, and under the supervised learning, there are two main sections. Either you do classification or regression. What's the difference between classification and regression? Classification is basically you provide labels, okay, to your data, or you identify the groups, okay, or the discrete classes, okay, for your data, right? So you identify the cluster and you give labels, okay. So normally you use this, for example, to determine whether on the image you have maybe 10 classes, all right, of land use, land cover, so you label them. So that is a classification. On the other hand, regression is basically you trying to determine the values, okay, the continuous values in the data. Okay, for instance, we can use regression in order to predict what is the value of the property over time, okay, or what is the value of the particular property, considering that there are certain parameters that we have in our data. Okay, so that is a regression. So regression is dealing with the exact values of phenomenon. Okay, so like a value of property, a value of the yield of crops, okay, or a specific value of the strength of materials and things like that. Okay, so that is a regression. Okay, that is different from classification. Okay, so for our class, we are going to do classification, okay, of our image, okay, because we want to know what are the labels on the ground. Okay, are they belong to we call it maybe soil or vegetation or urban or roads or things like that. We want to determine that. Okay, so that is the purpose of our mapping, okay, that we are going to do in our class. Okay, so far you have any questions? You have any questions so far? Right. You have the workshop at 10 o'clock, right? You have also registered. So I encourage you to attend the workshop, so that through the workshop you will have some understanding about what is Python, okay, what is machine learning, even though they are not going to work specifically on image classification, but at least the principles, okay, are still the same, and you can use that your knowledge from there, okay, and apply that in our specific we call it problems that we have during our course. Okay, so when we talk about classifiers for image classification, okay, we can classify the classifiers into two types. There are parametric and also non-parametric. Okay, the parametric classifiers are not based on machine learning. Okay, and the parametric classifiers are normally for hyperspectral classification are not very suitable because there are certain limitations. Okay, for example, they will suffer if the data dimension is very high. Okay, for example, hyperspectral data got very high dimensionality. Okay, because we have lots of bands. Okay, and with a huge volume. So normally, a maximum likelihood, as an example of a parametric classifier, will perform quite poorly. Okay, in that sense. Okay, so non-parametric classifiers were invented to overcome, okay, the limitations of parametric classifiers. And non-parametric classifiers are based on statistical properties of the data. And normally the non-parametric classifiers will involve the use of ground truth or the training and also the testing data. So this is what we are going to use later on. And as I have already mentioned, specifically we are going to focus on the use of support vector machine and also random forest. Okay. A support vector machine is a classifier that is based on the separation of the data that we have. Okay, so in a support vector machine, the purpose of this algorithm is basically trying to find what is the boundary, what is the optimum boundary, okay, that can be used, okay, to separate between different what you call it data classes that we have in our data set. Okay, that's the simplest way to explain about it. I don't want to dwell on the technicalities of the SVM because I don't want to make it much more complicated. Okay, but through your practical sessions later on, you will see that the support vector machine classifier is going to be affected by several parameters, or in remote sensing we call it, or in machine learning we call it hyperparameters. Okay, for example, what are the parameters for the C, what are the parameters for the kernel, what are the optimizer that you use, and also what are the types of the kernel. So all this will play a role, okay, in determining the effectiveness as well as the accuracy of your support vector machine, for example. Okay, so yeah, so these are all the types of kernels. For example, we have linear kernels, the RPF, the polynomial, as well as the sigmoid, and all these different kernels will have effects, okay, on the way the data are being classified. So in order to determine which one is the best or the most optimum parameters, we need to do experimentation. Okay, and then we need to use the training and also the testing data in order to get the statistical output, as well as we as the analysts, okay, we have to, we call it, analyze the image classification output, okay, from the data. Okay, so in QGIS there are two. At the moment, there are two plugins that we can use to classify our hyperspectral image or multispectral image. The first one is called Nmap, and the second one is called we call it the Avius. Okay, so Nmap was developed earlier than Avius, so Avius is quite new as a plugin to QGIS. So you can investigate, okay, which plugins are more effective. Okay, there are some differences in terms of the way they manage and analyze the data, right? And also the way they set the parameters will be different, or will be slightly different if there are certain familiarities. Okay, so you can experiment on that one. Okay, so in Mmap, for example, you have to select, for example, the kernel types. Okay, you have to select the techniques that you want to use for finding the optimal parameters and so on. Okay, so these are this is a method called cross validation. Okay, the careful cross validation. Okay, the careful cross validation is a method that is being used to analyze the accuracy of your model. Okay, this is the method that is being implemented in Nmap as well as in Avius. Okay, and this method is actually better than traditional methods of just training and testing split. Okay, so you're going to see what are the impacts, how you're going to use that. Okay, and this is the Nmap box plugin in QGIS that you will be using. So they will be using Nmap and also Avius, isn't it? For the hands-on.
Yes, okay.
Okay,
Yeah.
so they will be testing both, or they will be using only one?
They will be using both Nmap and Avius.
Okay. All right. So later on, Mr. Yuhao will be guiding you, okay, on how to use Avius or Nmap. We'll be using hyperspectral data from Houston because we have some data. Okay, for example, this one is the Japanese data. The Japanese data maybe because this is a civil engineering class, this Japanese data is more of an agricultural area. Probably you want to see data that comes from much more maybe like urban environment where you have a lot of man-made materials, infrastructure, and so on. So for that, we are going to use Houston hyperspectral data later. So when you do a classification or analysis of hyperspectral data, this is the standard flow that we'll be using. But the pre-processing part, you don't have to do because we have already done this part for you. Okay. Except maybe for the Houston data, maybe if it is in radians, you have to convert that into reflectance probably. Do you need to do that, Yuhao, or you have already converted them to reflectance already for the students?
Yeah, that I have converted into the using quick atmospheric corrections.
Okay, so Mr. Yuhao has already done the pre-processing for you, so you didn't have to do the pre-processing. We can skip that part, okay, because what is more important for you is to understand what is happening during the classification process, okay? So we will skip the pre-processing, okay? Yuhao has done that for you. So the data is already been converted into reflectance. So at the end of the day, probably what you will do is that you will do some experimentation and trying to analyze and discuss what are the impacts of the use of different parameters for the classification. For example, my previous students, they have analyzed the impact of the use of support vector machine on Landsat imagery in order to map a wetland area or a coastal area in Langkawi, for instance. Okay, so we publish a paper based on that. So you can also do the same. In fact, if you do a very good work on analyzing and discussing your work in doing the classification, you can also produce maybe at least a conference paper, or even if you can write properly, you can also publish in a good journal paper. Okay, so we have support vector machine. Support vector machine, as I have already explained, is based on the principles of finding the optimum separating plane, okay, between the different land cover or land use types in the image. On the other hand, you can also use random forest. Random forest is an assemble method, which is basically it is an assembly of decision trees. Okay, so it is using a different rule compared to support vector machine for the analysis of the data. So basically, it's based on certain rules created in the algorithm in order to determine the specific classes that we have in the image. Okay, so you can use a random forest as well in Nmap or in Avius. Okay, and you can see what are the impacts of the different parameters. Another thing that is also interesting for you to take note is the use of the artificial neural network. Okay, so if you go through the literature of machine learning, you will find mostly support vector machine, random forest, neural network, and this neural network is going to lead into deep neural network or deep learning. Okay, but the basis of deep learning algorithm, maybe some of you have come across this particular algorithm. Deep learning is a very popular algorithm nowadays. Okay, that has been used a lot for AI application, especially for real-time applications. Let's say, for example, for Tesla, for anything that requires real-time processing of the data. Deep learning is very effective. Okay, because deep learning got certain characteristics that are more advanced compared to support vector machine or random forest. Okay, support vector machine, random forest, and neural network are considered as the traditional machine learning. But we have recently the deep learning that was developed as an extension to the neural net, as an extension to the artificial neural network that can perform even better. Okay, compared to the traditional machine learning algorithms. Okay, and later on, after you have done your classification or during the process of classification, okay, you need to do some accuracy assessment in order for us to know what is the quality of the model that we develop. Okay, so this process is known as an accuracy assessment. So we call it in a practical sense, you can do accuracy assessment on the testing data as well as accuracy assessment on the predicted data as well. Okay, but your model accuracy is normally being calculated based on the testing data. Remember that you during your training and testing, you have, when you split your model, when you split your ground truth, you have the training and also the testing. Okay. Okay, so these are some of the examples of the previous work of my students, okay, on how they compare, for example, spectral-based and OBR. But OBR I'm not going to touch today. Okay, I'm just going to give you an example of, for example, object-based image analysis can perform better compared to spectral-based analysis because the object-based image analysis can identify the segments, okay, in the image. So it could be better compared to spectral-based. Nowadays, deep learning also can operate similar to OBR. Okay, so we are going to see what will be the impact. So there are a lot of algorithms out there, okay, that can be used, okay, for classification of hyperspectral image. So today I have gone just very briefly on some of the common classifiers that we can use. Okay, for example, the support vector machine and also the random forest as two examples of conventional remote sensing classifiers. And I have already mentioned to you about deep learning, okay, so that you are aware. So if you go to the literature and try to read through the papers and journals, okay, you will not be so, we call it, so shocked to see the term deep learning. So deep learning is basically just an extension to the artificial neural network, but it is more intelligent compared to the normal artificial neural network. Okay. So you can try deep learning as well if you have the time, if you have the resources to do that. What is interesting about Avius is that they have the deep learning modules, okay, for mapping, which is not available in Nmap. Okay, so in Avius, you can experiment using some machine learning models that are already being developed over there. Okay. So I'm not going to go too deep on that one. I'm also planning to do or to show you on how we can do data fusion, probably after the semester break, because next week we are going to have the exam, or sorry, the test one. Okay, so next week we're going to have the test one before the semester break or the Hari Raya break. And after the break, we can discuss about LiDAR data. We have a LiDAR data also accompanying the Houston data set. You have checked the LiDAR data? Have you checked the LiDAR data with Houston?
Yeah, doctor, I haven't checked yet. I will check later.
Okay, so no problem. So we have the data with Houston. So hopefully, if everything goes well, we can also use the LiDAR data provided together with the hyperspectral data of Houston. So maybe what we can do is that we can do image, we call it data fusion. Okay, we can fuse the hyperspectral data and also the LiDAR data together in order to create a 3D model of the study area, so that you have both the elevation as well as the spectral information being fused together. We're going to see whether we can do that. I mean, because we have just got the Houston data. What is interesting about the Houston data is that the data is being provided together with the LiDAR data set. Okay, so probably we can do data fusions later on. Okay, so I'm going to elaborate on data fusions towards after the break. So what I have already explained today, despite being very brief, okay, because we are going to have another session today with Python and machine learning. So we have discussed about several classifiers that are commonly used in image classification of remote sensing data. At the moment, there is no specific classifier that we can just say that, okay, this is the classifier that we can use directly in our process. No, there is no such thing. Okay, what you need to do is basically you need to experiment, because there is no guarantee that even though support vector machine might work very well in one case, in a separate case, but in the specific case that you have for your particular project, you might have a different data. The data might have different characteristics. So the support vector machine that are being defined for different project might not be useful or might not be directly transferable to the new project that you are working on. So you always have to experiment every time you have got a new data, because the characteristics of the data will determine how the models or how the algorithms are going to interact and perform the classification for you. So there is no classifier that will consistently provide the best performance throughout any sort of different projects and so on. So you always have to experiment. So when you do the experimentations, there are a lot of things that you have to consider. For example, the characteristics of your training samples, what are the tuning hyperparameters that you use, and what are the specific applications that you are working on. Okay, so for the exercise, we'll be using hyperspectral image together with Nmap, okay, as the plugin, or maybe we are going to use Avius as well in quantum GIS. Okay, so that is what we are going to do with how later on. So probably because we are going to join the workshop in a short while. Before we stop and jump into the workshop, you got any comments or anything you'd like the students to know, okay, before the practical part?
Yeah, Doctor, I would like to share the data now. The hyperspectral data. Just a moment. Okay, let me share the Houston data. Okay, okay, you all can access to the Google Drive link to download this Houston data. I have subscribed into 1.5 GB, and I also share the practical slide in the WhatsApp group. Okay, so Doctor, now perhaps I try to share some of the MNet interface and progress in the GIS.
Sorry again, what do you say?
Yeah, Doctor, shall I share the screen? I mean, to display some of the MNet interface and areas.
Okay, so yeah, maybe because the workshop is going to start very soon. You have registered. I think everyone has already registered, right? For the Python machine learning. Because later on, after the semester break, we are also going to use Python, okay, for training our models. Okay. So hopefully from this workshop, it is a free workshop. So hopefully when you go and join the workshop, you will get some exposure on what is Python and what is machine learning. So I think that could be useful for us. So maybe for the practical part, okay, maybe you can explain later. Is that okay? Because I'm not sure whether they have already started or not. They are going to start very soon, I suppose. Or if you want to quickly show the image, you can do that. Or if you want to just introduce them to the Houston data. You want to do that? You want to show your Houston data, Yuhao?
Yeah, perhaps, Doctor, I just quickly show the Houston data and import the Houston data and some of the MNet and areas interface.
Okay,
So,
you can do that very quickly.
Yeah.
Also, the students, you have to make sure that you have, you have downloaded QGIS and so on.
Okay. Can you all see my monitors?
And also at the same time, you can click on the YouTube live because they are about to start.
Yeah. Can you all see my screen?
Yes.
Okay. Okay. I have shared the Houston data. Later on, you can just import the Houston data by add cluster and also add vector layer. Later on, I will share the ground truth. I will share again the Google Drive link, the ground truth. And basically for the MF, again, it is because I have explained before how to install the MF, so I didn't explain it here. But uh, all of the handout I have all of the guidelines today I have provided, you can refer to that later. So basically, this is the MF interface, and for the classifications, we can just go to classification workflow. So this is the random forest and so on. So you can get that in the in the uh, in the slide that I have shared just now. And beside, uh, I I also have shown how to download various plugins, but in the slide, the latest slide I have put inside. So later on, you guys can go to just classify and supervise and to choose on the classification workflow. So basically, this is the areas and map plugin. I think that's all for me. Since
Yeah.
we are
So
running.
later on, you can also share with them the characteristics of the Houston data so that the students can understand. Last time we have got the PDF from the PDF information, the information on PDF, right, from the data provider. So we can share with the students as well so that they know what are the characteristics of the hyperspectral sensor, what are the characteristics of the LiDAR data, what are the characteristics of the platform, all right, so that they understand, the data acquisition properties.
I will re-update again in the Google Drive that I have provided later, the link I have.
Okay, and this data also, what is interesting about Houston data, as I already told you, they have the LiDAR data set together with it. Okay, so why LiDAR is important? Because LiDAR will give you the 3D component of it. Okay, so guys, I think they have just started. You can join the workshop now. Okay. So
Okay, Doctor.
yeah, so for us, this lecture from my side, we can end here. Okay, we continue with the lecture from the industry about machine learning and Python now. Okay, please everyone join.
Okay, Doctor.
All right, I'll see you next week then for your test, yeah. Okay, so thank you. Selamat berpuasa. Have a good weekend. See you next week. Okay, thank you.
Thank you, Doctor.
Thank you, Doctor.
Thank you. Okay.